Now we're going to be going over geometric sequences and series. So before we start, if we remember, the arithmetic sequences and series can be thought of as linear. They're essentially linear. The sequence is like a linear function. For a geometric sequence, it is similar to an exponential function. Okay, so we'll see that in a second. So let's start off with a geometric sequence. A geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a constant non-zero real number, and this is called a common ratio R. So arithmetic sequence, we added a number called the common difference. Geometric sequence, we're going to multiply a number called the common ratio. So if the common ratio of a geometric sequence is R, then the definition for a geometric sequence for R is going to be R equals A sub n plus 1 divided by A sub n. So this means that we find R by dividing terms that are right next to each other. You just have to make sure that the numerator is the term after the denominator. Okay, so that's how we find the common ratio. Just like we found the common difference where we subtracted terms, now we're dividing terms. And now next we have the nth term of a geometric sequence. So the nth term of a geometric sequence is given to us by A sub n equals A sub 1 times R raised up to the n minus 1. So we can see that exponential property of it with the exponent of n minus 1. So let's go ahead and do an example here. Let's find A sub 5 and A sub n for the geometric sequence for negative 12, 36, negative 108, and so on. So we can obviously tell this is not arithmetic because we can't just add a common difference to each one and keep on getting the next one. So clearly not arithmetic. So we know it's geometric. We know that we have A sub 1. A sub 1 equals 4 because that's our first term. And we know that A sub 2 is negative 12. So we can use these two terms to find our common ratio R. R is going to be A sub n plus 1 over A sub n. In this case, let's use A sub 2 over A sub 1. And we get R equals negative 12 over 4. So our common ratio is negative 3. So we keep on getting to the next term by multiplying by negative 3. So let's go ahead and find A sub n and A sub 5. A sub n we know is A sub 1 times R to the n minus 1. Let's go ahead and plug A sub 1 and R in. A sub n is going to be 4 times R, which is negative 3, to the n minus 1. So now we can find any term in this whole entire sequence, so pretty simple. And if we want to find A sub 5 now, A sub 5, we can use this formula. It's going to be 4 times negative 3 raised up to the 5 minus 1, which is going to be 4 times negative 3 to the 4th power. So multiply this out, and we should end up getting A sub 5 is 324. So that's going to be the 5th term. What we also could have done is recognize that we have 4 terms already. So we can just multiply the 4th term by the common ratio of negative 3. Negative 108 times negative 3 is also 324. Let's see another example. Let's find the common ratio R and the first term for the geometric sequence with a 3rd term of 20 and a 6th term of 160. So this one is definitely going to be a little bit harder here. So we know that A sub n for a geometric sequence equals A sub 1 times R to the n minus 1. And let's go ahead and just see what we know here. Let's say we have the third term. So the third term, which is a sub 3 equals a sub 1 times r to the 3 minus 1. That means a sub 3 equals a sub 1 times r squared. Okay, and then let's see the same thing for the sixth term. A sub 6 equals a sub 1 times r to the 6 minus 1. And that means that a sub 6 equals a sub 1 times r to the 5th, 6 minus 1. And one more thing we can actually plug in here. We know that a sub 3 is 20 because they gave it to us. And we know that a sub 6 is 160. Okay, so what we actually have here is two equations with two variables, and that means we can solve for these variables, which is exactly what we want because we're looking for r and a sub 1. So what we can do first here, we can take this equation right here and we can solve this for a1, and then we can take that expression and plug it into the other equations a1. It's essentially the substitution method. So let's go ahead and solve that for a1. All we have to do is divide both sides by r squared. We get a1 equals 20 divided by r squared. Okay, and now we're going to take that and plug it in. Plug in to make that arrow a little better. We're going to plug into this a1 and let's see what we get. So it's going to be 160 equals a1 times r to the 5th, and we plug in the expression into a1, which was 20 over r squared times r to the 5th. So now what we have is one equation with one variable, so we can solve this for r. And we can cancel two of the r factors and end up getting 160 equals 20 r cubed, or subtract the exponents, 5 minus 2 get 3. Divide both sides by 20. We end up getting 8, 160 over 20. And we get r cubed equals 3, or sorry, r cubed equals 8. And to solve this for r, we have to take the cube root of both sides. So r equals the cube root of 8. That means r equals 2. Okay, so we just found the common ratio, and obviously it's a little bit more challenging than maybe the common difference was to find from the arithmetic sequences. This was essentially the substitution method. And now we still need to find a sub 1. So let's do that over here. To do that, what we can do is we can use the a sub 3 equals a sub 1 r squared, which we know is 20 equals a sub 1 r squared. We know that r is 2, so let's go ahead and plug that in. And now we have one equation, one variable. We can go ahead and solve it. That's 20 equals 4 times a1. Divide both sides by 4. We get a1, the first term is 5. Okay, so when you are given two terms for a geometric sequence and you're looking for the first term in the common ratio, come up with two equations, two variables, substitution method, solve for the common ratio, and then use that, end up solving for the first term. Okay, so kind of a pain in the butt for that one. So that's a geometric sequence. Let's take a look at a geometric series now. As usual, a series is a sum of the sequence. So the geometric series is the sum of a geometric sequence. And if the geometric series has first term a1, common ratio r, then the sum of the first n terms is going to be s sub n equals the first term times 1 minus the common ratio to the nth power divided by 1 minus r. Okay, so once we know this little formula, it's pretty simple. So let's see this first example. Find the summation from I equals 1 to 6 of 2 times 3 to the I. Okay, so we could go ahead and plug in and do 2 times 3 to the first plus 2 times 3 to the second plus 2 times 3 to the third and so on all the way to the sixth. Or we can use this little shortcut here, and the shortcut is going to be s sub n, the sum of the first n terms, equals a sub 1 times 1 minus r to the n divided by 1 minus r. So let's see what we need here. We need n, we need r, and we need the first term. So the first term here is going to be found by plugging in a 1 into I. So that's 2 times 3 to the first, which is 6. So a sub 1 is 6. And r is going to be the common ratio, which is 3. It's the number that's being raised to the exponent. And we also need n. N is the value that we go up into, which is 6. So let's plug all of this in and see what happens. So the sum of the first 6 terms equals a sub 1 times 1 minus 3 to the 6th divided by 1 minus 3. Let's go ahead and evaluate now. That's going to be 6 times 1 minus 3 to the 6th power is 729 divided by negative 2. And keep on going here. We have 6 times negative 728 divided by negative 2. And we end up getting the sum of the first 6 terms is 2,184. Okay, so like I said, we could have actually done this by hand. It wouldn't have been too bad. It would have been 2 times 3 to the first plus 2 times 3 squared plus 2 times 3 to the third and so on. So it wouldn't take too long, but now we have this method. Okay, and now for the last thing here, we have an infinite geometric series. So that one was just finite that we did because it had a stopping point. So for an infinite geometric series, it may not seem like we can add up an infinite number of numbers and not get infinity, but we can. The sum of the terms of an infinite geometric series with first term a1 and common ratio r, the reason why we can add up an infinite number of terms and not get infinity comes down to the absolute value of the common ratio being less than 1. So if you keep on multiplying something between 0 and 1, where the absolute value is between 0 and 1, the number is going to be getting smaller and smaller. So if you add up numbers that are getting smaller and smaller, it won't always end up going to infinity. Sometimes it will, but it won't always. So the sum here is actually very, very easy. The sum of an infinite amount of terms here, where the absolute value of r is less than 1, is the first term divided by 1 minus r. Okay, so let's see an example of this. Find each sum. We have the summation for a here from 1 to infinity of negative 3/4 times negative 1/2 to the I minus 1. So obviously it's not even possible for us to actually add these all up. We would have to plug in a 1 for I, and then plug in a 2, and then plug in a 3, and we would have to do it an infinite amount of times. But now we can just use this shortcut. So we can say the sum of every term equals the first term times 1 minus the common ratio. So the first term, a sub 1, is actually right in front of us. It's negative 3/4. So if you didn't know that, you plug in a 1 into I. 1 minus 1 is 0. Negative 1/2 to the 0 power is 1, so we're left with negative 3/4. Now for the common ratio. The common ratio is the base to the exponential portion, which is negative 1/2. So notice here that the absolute value of r is less than 1, so we're good to go. So let's go ahead and plug this in. We get negative 3/4 divided by 1 minus negative 1/2. And maybe let's just do this one by hand just so we can remember how to simplify complex fractions. That's negative 3/4 divided by 1 plus 1/2, which is 3/2. And if we were dividing this is the same as keep, change, flip. Keep the first one the same, multiply by the reciprocal of the denominator. So we get negative 3/4 divided by 2/3. And we can see that these 3's cancel. We're left with negative 2/4, which ends up simplifying to negative 1/2. Okay, so if we added up all of the terms of this sequence here, we would end up getting negative 1/2, which is a pretty nice number compared to what we see here. So if this r value, if the absolute value of the common ratio is not less than 1, then this would diverge and we wouldn't even get a numerical answer here. All right, let's do one more. We have the summation from 1 to infinity of the sequence 3/5 to the I. And let's go ahead and write down what we're going to be finding. The summation of all of the terms is the first term divided by 1 minus the common ratio. And a sub 1 here, it's a little bit different. If you see how we had I minus 1 here in the previous one, this one has I. So it does get a little bit tricky with that index. But the good thing is all you have to do is plug it on in to find out what it's going to be. We plug in a 1, and this time we just get 3/5 as our first term. Our common ratio is also going to be 3/5. It's just whatever is being raised to the exponent, so 3/5. Let's go ahead and plug it in. We get the sum is going to be 3/5 divided by 1 minus 3/5. And let's go ahead and simplify it. We get 3/5 divided by, getting a common denominator in the big denominator is going to be 5/5 minus 3/5, which is 2/5. And doing some keep, change, flip here, that's 3/5 times 5/2. The 5's cancel, and we end up getting the sum is 3/2. Okay, so this ends up, if you added up all of these in the sequence, infinite number of them, and they actually only add up to 1.5. Okay, so that's it for this section. It's actually easier to find the summation for an infinite series than it is for a finite series most of the time, for geometric series. Okay, so that's it for this chapter.